This is how to find K and use Le Chatelier's principle to get a concentration that we like. An equilibrium mixture is 0.700 molar SO3, 0.910 molar SO2, and 0.520 molar O2. The first question asks, what is Kc? We're given our concentrations in molar, so that's pretty useful for finding the value of Kc. Let me write my values underneath in the reaction table. Alright, Kc is going to equal products over reactants raised to their coefficients. So that's SO2 squared, O2 to the first power, over SO3 squared. Now let me substitute my variables. I have 0.910 squared times 0.520 to the first power over 0.700 squared. This turns out to be 0.8788 units of molar if I put it into my calculator. And just to be concerned about WebAssign, I guess I should use 3 sig figs. So 8.79 times 10 to the minus 1 power molar is my value for Kc. The next question asks, how many moles per liter SO3 must be added to produce an equilibrium mixture that is 1.3 molar SO2? Alright, why don't I write my reaction here with my starting values. Okay, I am going to perturb the equilibrium by using Le Chatelier's principle. So I want to add some SO3, and the final outcome that I want is that my SO2 concentration will be 1.300. So I'm going to perturb the equilibrium by adding SO3. So I'm going to put plus X here in the initial row underneath the SO3. When I add reactant, I am going to make the reaction shift to the right side. Alright, if I know the initial row for SO2 and I know the final row for SO2, then I know the delta row. That should be 1.3 minus 0.91, or 0.390 molar, and that's plus, because the reaction is shifting to the right, and also the difference in math. What about the O2? There are 2 SO2s for every 1 O2, so that means I should be adding plus 0.195 molar O2. What about the SO3? Well, that should be reacting. So the ratio is 2 to 2, so that should be minus 0.390. Okay, now I just have to do my accounting. So for the SO3, my value comes out to be 0.410 plus X. Do not forget to bring the X down. Otherwise, you're left without a variable to solve for. You're asking, how much do I add? And X represents, how much do I add? I will also do this math for the O2, and that would be 0.715. Okay, now it's time to solve for X. So, I have my SO2 concentration, which is 1.300 squared, times my O2 concentration, which is 0.715 to the first power, and my SO3, which is represented as 0.410 plus X, quantity squared, must equal 0.8788 molar. Very well. I shall solve for x. The easiest thing to do is to rearrange this such that my x's are on one side. So I will write 0.410 plus x squared here, and then on the other side I need to write 1.300 squared 0.715 divided by 0.8788. Okay, so I've just essentially switched places for my x and my equilibrium constant. Now the easiest way to solve for this is to take the square root of both sides. On the left side, I have 0.410 plus x. On the right side, I wound up with 1.172. So, solving for x, x is equal to 0.763 molar. So that should be the amount of SO3 that I need to add to influence the equilibrium such that my SO2 is 1.300 molar. Part C of the question asks me for the Kp value given the temperature. So I will pull out that formula. Kp is equal to Kc times RT delta Ng. Alright, my Kc I have calculated. That is 0.8788. The R that I'm going to want to use is the ideal gas law constant, so that's 0.0821 liter atmosphere per Kelvin mole. My temperature is given to me as 323 Kelvin. And finally, I should find out delta Ng. Let's see, delta Ng, I'll write it down here, is equal to moles of product gas minus moles of reactant gas. So 3 minus 2 is going to give me a plus 1. Excellent. I will just point out that the 0.8788 is in units of molar, which is in units of moles per liter. So when I finally multiply this out, the moles and the liters and the Kelvin are going to cancel out, and I'll be left with units of atmospheres, which is excellent because that's what I was hoping for. And putting it into my calculator, my Kp winds up to be 2.33 times 10 to the first power units of atmospheres. All right, the last question asks for the free energy change at standard state given a temperature of 323 Kelvin. Very well, we will write down the formula, and that is delta G standard state is equal to minus RT natural log of K. Now, R, you know very well, is 0.008314 kilojoules per Kelvin mole. We know the temperature, that is 323 Kelvin, natural log of K. Now, perhaps you're wondering to yourself, which K should I use? Okay, at standard state, gases are measured in atmospheres. Aqueous materials are measured in molar. Let's look back at our reaction. What is the state of the materials in our reaction? Gas. So we are going to use Kp. So when I finish this equation, I should put in here 2.33 times 10 to the first, plus 1 power, as the material I'm going to take the natural log of. Putting that into my calculator, I am going to wind up with a value of minus 8.46, and that's in units of kilojoule per mole of reaction. That's all there is to that.